Electricity is literally magic. Like, if you showed someone from the 1700s your room right now, the moment they saw your RGB LED light strips, they'd probably be reaching for the old witch-burning steak. And honestly, can you blame them? They're still churning their own butter while pretty much everything in our life is powered by something we can't even see. But what is electricity really? First, we gotta talk about the tiny building blocks of everything. Atoms. You, me, the device you're watching on, all made of atoms. Inside every atom, you've got three main parts. Protons have a positive charge and chill in the nucleus. Neutrons have no charge and are also in the nucleus. Electrons have a negative charge, and those little guys are constantly zooming around the nucleus. Think of it like a miniature solar system, with the nucleus as the sun and the electrons as planets. Since opposites attract, the negatively charged electrons are naturally drawn to the positively charged protons. In a balanced atom, there's an equal number of protons and electrons, keeping the atom stable. But in some materials, particularly metals like copper and gold, some electrons aren't held very tightly by their atom's nucleus. These free electrons are able to jump from one atom to another with relative ease. So when we talk about electricity, we're talking about the organized directed movement of these free electrons. To get free electrons to move in an organized way and create electricity, three key concepts come into play. First up, voltage. Voltage is known as the electrical pressure or potential difference. It's the push or pull that shoves electrons from one point to another. More voltage, stronger push. Next is current. This is just the rate at which electrical charge flows through a material. The more electrons it's zooming by per second, the higher the current. It's measured in amps, and every amp means that about 6.24 quintillion electrons are passing through a point every second. Finally, resistance. Even in amazing conductors like copper, electrons aren't able to just move freely. Kind of like a person trying to move through a crowd to buy that TV on Black Friday, electrons bump into atoms and other electrons, creating friction and slowing their flow. Some materials have higher resistance, and these are called insulators. Their electrons are basically glued to their atoms, making it super tough for them to move and conduct electricity. It's good for keeping those electrons in place, but bad if you're trying to power your house. These three concepts are all linked together by this relationship called Ohm's law. But before you start asking your neighbors if they want you to rewire their entire house, bragging that you know Ohm's law, there's one more crucial piece to this puzzle. How does flowing electricity actually power stuff? The answer is all about converting electrical energy into other forms of energy. Take heat, for example. Your toaster and those old incandescent light bulbs, they're all about converting electricity to heat. When electrons flow through a material with resistance, they collide with atoms. Those atoms vibrate like crazy, releasing heat. In incandescent light bulbs, a super thin, high resistance wire gets so hot from all those collisions that it glows white hot, producing light. But this is extremely wasteful since most of the energy is lost to heat. That's why we have moved on to light-emitting diodes, or LEDs, which convert electricity directly into light. When electricity flows through the LED, the electrons move across a special junction inside the semiconductor and fall into empty spaces called holes, and release their excess energy in the form of particles of light known as photons. We can also convert electricity to mechanical energy using electric motors. When the electrons flow through a wire, they create a magnetic field around it. That's why compass needles freak out near a current-carrying wire. In an electric motor, wires are often coiled around an iron core to make super powerful electromagnets. Then, multiple electromagnets are arranged so that when current flows through the coils, their magnetic fields attract or repel each other, causing the coils to spin. Plus, since no one wants to find an extension cord long enough for a Tesla road trip, being able to store the electrical energy is also important. But batteries don't literally hold the electrons like water in a bucket. Instead, batteries take advantage of chemical reactions to store chemical energy. When you charge a battery, electrical energy is used to force a chemical reaction that stores energy as chemical potential. Then, when you discharge the battery by using it, the chemicals react in reverse, releasing electrons.